Hello there, and welcome back to our Chem 131 lectures. This is the part two for chapter two. And I just actually wanted to begin that. I have a quick picture here of the periodic table that I colored in for myself. This is the one that you will have for our practice session. I'll try to remember to bring in some colored pencils so that you guys can do this as well. But feel free to do something like this with your periodic table, and then and you can still use that on tests. It's just easier to see. Just make sure you don't color it in so darkly that you can't see the numbers because they're very small. All right, so now we're going to switch over. Now what you can see here is this section in your ion list, okay? So for this part of the lecture, you need to have this in front of you. Now, hopefully you had your periodic table in front of you for the last one, but go ahead and flip it over and you can see on here all of the different ions that we're going to be using. You can see monatomic cations and monatomic anions, and it gives you some hints up here. Some type 2 cations that we'll be working with out of our transition metals, and then those polyatomics that I mentioned. All right, so what we're going to do now is we're going to go ahead and go back to our slides. Hello. And I need to go into a slideshow. There we go. Hello. Okay, so here we are on slide 20, and let's go ahead and review a few things. All right, so first of all, I'm sure you're not reviewing, this one's new. I thought I was starting with something old, but I'm not. Okay, so first of all, let's look at organic chemistry. Organic chemistry is the study of compounds of the element carbon. And the interesting thing here is that, and we'll get into this later, but you might think, okay, well, I'm not going to be an organic chemist, I'm going to be an engineer, except that engineers have come up with this fascinating substance called carbon fiber. And carbon fiber is revolutionizing so many different things that used to be made out of very rare woods or heavier metals. So it's very, very fascinating and an important thing for engineers to be aware of. But organic chemistry also includes the naturally occurring biological materials and then many of those synthetic polymers like the polyethylene or the carbon fiber. So becomes very important. Inorganic chemistry is basically the study of all other elements except carbon. And in general chemistry, we actually focus a lot on the inorganic side of things. Since you guys are taking chemistry for engineers, there will be a little bit more of that in there, though. Okay. So now to take a quick look here, inorganic chemistry is going to have a few different things. So we're looking in here, we see our inorganic compounds that can exist as either covalent compounds, which are molecules, or ionic compounds. Now, this is a really important thing. Covalent compounds, remember, are discrete units like this silicon tetrafluoride, tetrachloride that you have here, the silicon tetrachloride. And that is a good example of an inorganic molecule. It exists as a discrete single unit, and you can have more of them, more than one of them. Now, the other option here is ionic compounds, and those are not molecules. Okay, let me go ahead and put molecules back in that purple. All right, so ionic compounds are not molecules. Remember, so here we have this sodium chloride, and you've got an example of it right here. They form that lattice structure. So the difference between molecules and ionic compounds is a big one. Now let's take a look at some of these inorganic molecules that we can work with. So there's different things to do, but one of the really important things that we're going to be looking at here is how the transition metal cations have what's called a variable charge. And on your ion list here, there are those type 2s. Those are some examples of them. And they can have really different properties. So for example, iron is on your periodic table. Iron looks like this, and I won't draw these for long, but since I don't have you in class, it's kind of helpful. So here's iron on the periodic table. It's number 26. It's a transition metal. It's Fe, and it's 55.845 for a mass number. Okay. Now, iron can form two different ions here. It can form iron 3, and iron 3 is Fe3 plus, which means it has lost 3 electrons. Okay. And that means that it has 26 protons and it has 23 electrons. And this up here is an example of an iron 3 chloride, FeCl3. And it's this orange brown color, it's a density, it's very distinct. Okay. And so now, though, you can also with iron form iron 2. We used to call this ferric and ferrous. All right. And now iron 2 is an Fe2 plus. It has lost 2 electrons. And so it has 26 protons and 24 electrons. And we think, okay, well, what's the difference? People say, why do I have to lose all my points if I don't include those? Well, iron 2 chloride, FeCl2, is this yellowy powder, okay? And these are really different. So it has to be right. So this is one of those places where basically you're either all right or you're all wrong, because if you grab the wrong one, that's a really big deal. Notice the difference here. The iron 2 chloride has a melting temperature at 670 degrees Celsius, and the iron 3 chloride has this 306 degrees Celsius. So also that's just a huge, huge difference when we're working with it. So be correct. All right, now this is an example of an organic compound. This is methyl methacrylate or plexiglass. Okay, and you can actually form organic compounds in chains that can grow up to 6,000 atoms long. And they're often shown as line structures, and this is an example of a line structure. You'll be seeing more of these in this chapter and in future chapters as well. Okay, and here you see some fun new things. Okay, so on the next page, one of the things that we're going to be looking at is we're going to be looking at some different things here. So here we have a C to a C single bond, and this part would be sort of like an alkane, and then because it has a single bond, then you've got 2 here for an alkene. Okay, let's look at some other things here. See this this O in the middle here. Okay, this O in the middle, and with here. Actually, let me do this in a different color. Okay, see this this C double. This is a carbon double bonded to an oxygen double bonded to another one here. This group is called an ester. Okay, so you'll see on the next one that we have different names for these. So here's some examples of some different ones that you can add to your notes. First of all, we have the alkyne, and it has a triple bond here. Actually, so it has this triple bond. And one of the things they didn't include in here is that a C double bonded to a C often makes an alkene. And carbon-carbon chain is an alkane. Okay, you have an alkyl halide, and an alkyl halide replaces all of this with a halogen, chlorine, bromine, iodine. Okay, whenever you see this R value, R means rest, of the molecule. And hang on. Rest of the molecule. And it's just so you're only looking at one. An alcohol is an OH, or an oxygen hydrogen group. A carboxylic acid has this at the end. You have the rest of it and a C double bonded to an O and an OH. You have a ketone that has just that, double bonded to oxygen. And now instead of a carboxylic acid, if you don't have an OH here, but just an H, you have an aldehyde. Now, in the middle of something, if you in the middle of something, you have something that looks like a carboxylic acid. This is an ester. And an oxygen in the middle like this is an ether. And you'll have heard many of these terms within other things. All right, so now let's get into naming, and this is where you're going to need those naming things right here. As I go through these, please make sure that you are pausing and you are looking and you are finding. That's going to be really, really important when you're studying. Okay, so binary compounds are composed of two elements. You can have binary ionic compounds like sodium chloride or magnesium chloride, and these are always metals to nonmetals. And you can have binary covalent compounds, and these are going to be a nonmetal with a nonmetal. And ionic compounds and covalent compounds are named differently. So that first thing that you need to do is look for a metal. All right, so let's start with naming our covalent compounds. Okay, so when we're naming a covalent compound, remember that the big thing here is that there are no metals. All right, and you've got that chart with it made there. All right. So the important thing to think about here is that we have no metals. Okay, and always be watching for that no metals part there. Okay. So now the first element is going to be name. You know what? You probably can't see this. Let me see. Your one is going to be mono. I don't know if you can see it if things are in the way on the screen. Two is di, three is tri, four is tetra. Okay. And we've got penta. Six is hexa. Make sure you're writing these in. Seven is hepta. Eight is octa. Nine is nona. And 10 is deca. Okay. So now let's take a look at what we're working on here. It says prefixes precede each element, except that mono is not used for the first element. So we're going to be working with that. Again, you have to have your periodic table here. And you see this nitrogen. I'm going to start with this. We see nitrogen. And then oxygen becomes oxide. You'll see, I'm going to leave a big space here and you'll see why in a minute. Nitrogen and oxide. Okay, now we have this two here, right here, and two over here is di. So this becomes dinitrogen. And then we can see the five here, and over here we see five is penta, dinitrogen. And then instead of writing pentaoxide, we'll just write pent. So we get dinitrogen pentoxide. And you probably would not have a capital letter here in the dinitrogen. So dinitrogen pentoxide. Great. Okay. Now on the second one, we see a P, and that's phosphorus. And then the Cl is chlorine, which becomes chloride. Now, if this were somewhere else, it would be monophosphorus, but we don't use mono on the first one. You could use it later, like for example, CO becomes carbon monoxide. Okay. All right. So now you see this 3 here on chlorine. Okay, and 3 is tri, so this becomes phosphorus trichloride. Okay. All right, now let's do the last one here. We've got P, and then we have O here. Okay, so I've got phosphorus, and I have oxide again. All right, and now here you can see the 4, and so that becomes tetra. And again, you wouldn't need that capital, but tetraphosphorus. And then you can see hexane, so that would be hex oxide, just like that. Okay. All right, great. Now here's some other examples here that you can put some of these in your list. Here we have, so every time that you see, so these are ball and stick models. Okay, so let's go ahead. The blue ones here are nitrogen. Okay, and the red ones are oxygen. Okay, so here you can see that you have 2 and 1. So N2O is dinitrogen monoxide. And here you have nitrogen monoxide here for B. C is nitrogen dioxide. D is dinitrogen trioxide. E is dinitrogen tetroxide. And F is dinitrogen with 5 pentoxide. Okay, so that's how you would name these, as just a little bit more of an example here. Okay. So here we have our binary ionic compounds, and we're going to start with what we would call type 1, or type 1 with metals. Okay, the cation is named first and the anion second. And people will say, does that matter? And the answer is yes, it does. The cation goes first, that's the positive one, and the anion, the negative one, goes second. The monatomic cation takes its name. Oh, the monatomic cation takes it is okay. This should be has the same name as the element. I'm not sure what I meant there. Okay. The monatomic cation has the same name as the element, and a monatomic anion is the root of the element name plus "-ide". Okay, so what we're going to do is let's take a look at what we've got going on here. Let's work a little example on the side first, and then we'll go from there. So first of all, if I have NaCl, and if I look at my my ion list, I see that that's sodium ions and chloride ions, and they balance 1 to 1. So that becomes sodium chloride. Okay, and then I can go back in the other direction, and I can say, okay, let's take a look and instead work from the name backwards and say that we have gallium oxide. And when we look at our ion list, we see that gallium is Ga3 plus and oxygen is O2 minus. So what do we do in this situation? Well, we will take this 3 and we'll bring it down here, and we'll take this 2 and we'll bring it down here. And that becomes Ga2O3. Now, if you're wondering how that's going to work here, okay, let's take a look here. So see, you have 2 galliums, and each one is a 3 plus. So that means that you have 1, 2, 3, and 1, 2, 3, for our positives because we have 2 galliums and they each have 3 positive charges. Now we have 3 oxygens and each one has 2. So we have 1 oxygen and another oxygen and another oxygen. So now you can see that when this balances, we have 6 positive charges and 6 negative charges, and they have to do that balancing. Okay. So now let's take a look at what we have here. So you're going to find your cations as your positive charges and your anions as your negative charges, and you're going to find them on this ion list. Okay, so we can see that our cation is a K plus for this, and our anion is a Cl minus. And that means that we can find these names again on our ion list. So that becomes a potassium chloride. Okay. This Mg and this Br. So I have Mg and Br. And if I look these up on my ion list, I see that magnesium is a 2 plus. And again, you should be pausing. You should be finding every single one on your ion list. If you're not familiar with those ions in your ion list, you will not be able to use them when it comes time to take the test. Okay. And Br minus. And you can see that this 2 right here ended up right there. Okay. So this becomes magnesium bromide. Okay. This Ca and an O. So here we have Ca and O, and we see that this is Ca 2 plus and O 2 minus. And those 2's balance each other exactly, which is why we don't have any subscripts. And so this becomes calcium oxide. Okay, now let's work it in the other direction. So first of all, we've got beryllium, and we can see on our list, our monatomic cations, that beryllium forms a Be2 plus, and fluoride makes an F minus. All right, so I bring that 2 plus down, and this becomes BeF2. All right, now I have my aluminum sulfide, and I see again on my ion list that's Al3 plus, and sulfide is S2 minus. And I bring that 3 comes down here, and that 2 goes down here. And that means that I have Al2S3. And the last one on this page is I have strontium, Sr, and it's a 2 plus, and phosphide is a P3 minus. Okay. And when I bring those down as well, this becomes Sr3P2. Okay. And so that's how you go from formulas to names and back again for your binary ionic compounds. All right, now we have our type 2 binary ionic compounds, and these occur when you have a metal with more than one charge. Okay, so metals, so these are going to be transition metals, and they're going to also be what I call heavy metals, and sometimes they call them post transitions, but not all of them. So you're looking at basically things like indium, tin, thallium, lead, bismuth, and polonium. Gallium, germanium, and aluminum are monatomics. They only form a single type 1. Okay, so transition metals plus are heavy metals, call those, like lead. Okay. So let's work through this. Now, you can see that what we need to do now is we need to take a look at what we're working with. Now, with these, Oh, first of all, don't forget to add these on in your cheat sheet. 1, 2, 3, 4, 5, and 6. People sometimes will get it wrong because they don't have those memorized. So put those on this as well. Okay. Okay, so when you're working with this, start with your anion. And you can see that Br there. And here we have Br. And we know that Br is only a 1 minus charge. See how these match? Here you have just one copper and one bromine, or I put it down here, one copper, one bromine, they're the same. Okay, that means that in order for this to match, your copper has to be Cu plus. Now, if you look at your ion list, you can see that Cu with a 1 plus is copper 1. And so it's copper 1 bromide. All right. And now we have our FeS. Now, sulfur has to be S2 minus. Now you can see that your iron and your S, they balance. See, there's only one of each one of them. So this has to be an Fe2 plus. So this has to be iron 2 sulfide. Okay. Now let's take a look at what we're having here. Now, you'll notice on here that there's two kinds of oxygens. There's oxides and peroxides. It's usually best to assume that you have an oxide unless you can't have an oxide. And then you could say, okay, well, it's a peroxide. In this case, we're going to assume that it's just a regular oxide because peroxides aren't very common. Okay. O2 minus. Now, there's two of them. So that means that if you have two of them, O2 minus and O2 minus, then you need to balance that out with 4 positive charges. 1, 2, and 3, 4. There we go. Okay. So that means that this has to be Pb4 plus. Okay. And so that is lead 4 oxide. Now it's all easier going in the other direction. Iodide, we know from our ion list, is I minus. Iron 3 just means Fe3 plus. I bring the 3 down, and so this becomes FeI3. In cobalt 2 oxide, cobalt 2 is CO2 plus, and oxide is O2 minus. And you can see that these balance perfectly. So this is just going to be COO. Notice that my lowercase o is small and my uppercase O is big. That's also really important. If these are the same, I will take points off for that as well, because it's just very important that this be legible. So dial back your handwriting a little bit and make sure that it is neat on this section, because if I can't read it, it's wrong. All right, then we have titanium 4 phosphide. And phosphide is a P3 minus, and titanium 4 then would be Ti4 plus, and these would come together as Ti3 P4. Okay. All right, now let's take a look at some polyatomic ions, and then we will be done. That's the good thing about you engineer, instead of my general chemistry classes, they also have to name acids and bases, and that's actually pretty tricky. All right, so let's take a look at what we've got going on here. Okay, these ionic compounds with polyatomic ions. So let's take a look at working through one of these. Okay, so first of all, let's look. It's not one of the ones on here, so let's take a really, really great look here at a couple things. So first of all, you'll notice that I want you all to find hydroxide. Okay. Hydroxide is an OH minus. Okay. So that means that it's an OH with an overall minus charge. You're going to see that we're going to need some parentheses in here. So we're going to be doing a calcium hydroxide. And calcium hydroxide, not hydro. There you go. Calcium hot. Oh, it was. Okay, hang on. Calcium hydroxide. There we go. I'm spelling correctly. Calcium hydroxide is a Ca2 plus and a hydroxide OH minus. Now, in order to identify that we have two complete hydroxide units on there, this becomes Ca, and then we have to put this in parentheses for 2. Again, if you do not have the parentheses, then it is wrong because that means CaO and then 2 hydrogens, and that's not a thing. So you have to include the parentheses when the whole thing gets doubled. Let's do a couple of other little things. Another reason why names are just so important is because we're going to look at potassium with sulfide. Okay, so potassium sulfide, potassium sulfite, and potassium sulfate. Okay, so you notice that these are very similar. So potassium is K plus, sulfide is S2 minus, so potassium sulfide is K2S. Sulfite is SO3 with a 2 minus charge. So potassium sulfite is K2SO3. And sulfate is SO4 with a 2 minus charge. So potassium sulfate is K2SO4. So again, if the spelling is not correct, these are very different compounds, even if they look a little bit similar, if the spelling is not correct, it is wrong. So make sure that your spelling is correct in this place. It is just really important that those be correct. All right, so now let's take a look at what we're working on here. So this first one we can see starts with the cation sodium, and then it has the anion with an OH minus. So this becomes sodium hydroxide. All right, so now looking at your ion list again, you can see this NO3. It's listed with a 1 minus charge, okay? And there are 2 of them, which is a way to help you see that then the magnesium has to be with an Mg2 plus. And this is magnesium nitrate. Okay. And you have NH4 with a 2. Now, this is one of our only polyatomic cations. It's NH4 with a 1 plus charge on it. And your SO4 is SO4 with a 2 minus charge on it. And you can see you've brought this down, and that's in parentheses. So this is ammonium sulfate. All right, now let's go back in the other direction. We have iron 2 phosphate. So we know our type 2's iron 2 is Fe2 plus. And phosphate is PO4 with a 3 minus charge. Again, be pausing and looking for these on your sheet. Okay, and when we bring this together, this becomes Fe3 PO4 2. Okay, and that's because just like before, we brought our 2 down here and our 3 down there. Okay, now we have sodium thiosulfate. Well, the sodium is easy, Na plus. Then we have to stop and we need to take a look and see if we can find that thiosulfate. And thiosulfate is S2O3 with a 2 minus charge on it. Okay, and when we combine these, that becomes Na2 S2O3. We're bringing that 2 down. And then last, we have silver chloride. Silver is a transition metal that only forms 1 cation, and it's Ag+. And you can see them on the side in bold. There's 3 of them that only form 1 each. Okay, and then our chlorate is Cl O3 with a 1 minus charge. These will balance perfectly, and silver chlorate is AgClO3. All right. This is a great chapter to make sure that you're reading it and really paying attention. It's definitely pretty challenging. All right. Okay. Oh, that was slide 30, by the way. I thought I had numbered them all. And I must have forgotten. That was slide 30. I missed one. Okay. So now let's take a look at that polyethylene that we had been talking about at the beginning. It's the most common synthetic polymer in the world, and it's found in various forms. Polyethylene can be found in items ranging from plastic grocery bags to children's toys, automobile gas tanks, and even bulletproof vests. And it is one of our carbon things that we're going to work with here. All right, so just as a review, ethylene itself is looks like this. It's an HCH double bonded to another one. Okay, this is ethylene. Okay, C2H4, and it's going to form polyethylene. Okay, and basically what we're going to be doing here is we're going to be attacking out this double bond and making a long chain. So let's take a look on the next slides to see how that polyethylene is made. Okay, so here is the reaction. Okay, and what we're going to be doing is we're going to be using a small amount of an initiator. And so we use that with what we call these R dots. So see this? This is a free radical. And a free radical exists when you have an unpaired electron. It's an extra electron. Electrons need to be paired when they are in or shared in that pairing. And so whenever you have a free radical like this, it is highly reactive and it will continue. So what happens is that this right here, this R attacks in here and takes out the double bond. And now it's here. So this double bond, one of the electrons comes here to pair with the R value, and the other one comes out here, and you see it here. Now, all of a sudden, this is a radical, and it can attack another ethylene molecule like this. So what happens is that this double bond comes out here. Okay, so I can erase this second double bond like that and draw a bond up to there. The second electron from that double bond comes here, and now it's ready to attack another one. And that's how you make this polyethylene, is with this kind of this chain reaction. All right, so here you can see it occurring again, and this is just what I had drawn on the previous slide. So that attacks that. Now you have a 4 chain, and you continue and continue and continue. This keeps going on and on and on until you end up with the polymerization occurs until either the free radical end here of the growing reacts with another free radical, which terminates the growth chain. So you could actually say, okay, well, here's an R and here's an R, and you can see that there are no, so two of these come together. So basically what you have is you have this one with its dot here attaching to another one with another dot like this. They come together and all of a sudden, boom, you have this whole thing. And that's how that gets terminated. And for our last slide here, these are just some different versions of polyethylene. It's not always so neat and tidy. You have polyethylene polymers that, let me see. Hopefully, I think you have this. Let me, polyethylene polymers can be, hopefully you can see that can be in linear chains. So this would be this is a linear chain here, because it's in a line. And this is an example of a high density polyethylene, or HDPE. Or you can have, instead of linear chains, you can see it comes off like this. And this one is called a branched chain. Okay. and that might be an example of a low density polyethylene. You can also have extremely long linear chains right here. Okay. And this might be an example of your very, very long chains, maybe a ultra high molecular weight polyethylene, which just has really, really long chains going on. Okay, so branch chains over here and linear chains over here. All right, I look forward to seeing you in class. Let me know if you have any questions.